Hello everyone, welcome to this lecture. Just a quick recap, in the last lecture we had seen how to use hash functions, collision resistant hash function to create message authentication codes for arbitrary long messages. So, the plan for this lecture is as follows. In this lecture we will discuss birthday attacks, which is a class of generic attacks which can be launched against any hash functions. And we will also discuss the small space birthday attacks for finding collisions in hash functions, and finally we will discuss some of the other applications of hash functions apart from the message authentication codes. So, let us start with birthday attacks for finding collisions. So, imagine you are given a deterministic hash function which is publicly known, then the naive algorithm for finding collision in this hash function is as follows. You can evaluate this hash function at 2 to the power L plus 1 number of distinct inputs, and it is guaranteed that with 100% probability or 100% success you will obtain a collision. The success probability of finding the collision here is 1. This is because of the pigeonhole principle, because in the worst case, at the best you can hope that 2 to the power L distinct inputs go to 2 to the power L distinct outputs. But since you are evaluating your in H function at 2 to 1 more input than 2 to the power L inputs, then definitely there will be 2 inputs which will be giving you the same hash value, and that will give you a collision. So, the success probability of this naive collision finding algorithm is 1. It gives you a 100% success guarantee, but unfortunately the running time of this naive algorithm is of order 2 to the power L, and if little l is significantly large, then of course this naive collision finding algorithm is impractical. So, now let us see a generalization of this naive algorithm, and the generalization goes as follows. You evaluate this hash function at q distinct inputs, which I denote by x sub 1 up to x sub q, and you obtain the hash values, and you pass these inputs comma output values and check whether exists a pair xi comma xj such that their hash values are same. Now, we are interested to argue here what is the success probability of this generalized algorithm. So, remember, if q little q is said to be 2 to the power L plus 1, then basically this generalized algorithm becomes a naive algorithm. In that case the success probability is 1. But now your q need not be 2 to the power L plus 1, it could be any function, and now our goal is to analyze the success probability of this naive algorithm as a function of q and the size of your hash domain, so the size of your hash function, right. So, while doing the analysis, what we will assume is that the function h is behaving like a truly random function, and why so? Because that is the best you can hope for, because if indeed your function h behaves like a truly random function, then that is the most difficult task for the adversary, where the adversary's goal will be to find a collision, because it can be proved that the probability of finding collision for this generalized algorithm gets better if your underlying function h is a non-random function, and if instead of querying on distinct inputs x1 to xq, your algorithm makes queries for random set of x values, right. So, we are basically actually not making any stronger assumption by assuming that the function h is a random function, because the success probability of this naive algorithm is lower bounded by the success probability that this naive algorithm will give you for the case where we are assuming your underlying function h is a random function. So, let us set the setting for the generalized case here. So, you are given a truly random function from the set of binary strings to a fixed domain, where the size of the domain is big N, and say you have made q number of queries for these hash values on distinct inputs x1 to xq, and the corresponding output values are y1 to yq, and since I am assuming my hash function is a random function, each of these y sub I values are uniformly random values from the set of big N values which my hash function can throw as the possible output. And I denote the event call q comma n, the event that there exists a collision, namely there exists a pair of indices I comma j where I and j are different, but the corresponding hash values, namely yi and yj, are equal. And my goal is to compute a lower bound on the probability of this event collision q comma n. So, I want to prove here that if the number of queries that I am making here is upper bounded by square root of 2 times n, then the probability of collision is at least q times q minus 1 over 4 n. So, let us see how we can derive this. So, let me denote the event no collision sub I to be the event that when we are making the first I, when we have made the first I queries, all the hash output values are distinct. That means the y1, the values y1, y2, yi are all distinct. If that is the case, that means h of x1, h of x2, h of xi, they are all distinct and no collision has occurred, and that is the event no call I. And it is easy to see that since we are making q number of queries, then the event no call q is basically the complementary of the event collision q comma n, because if the event no collision q occurs, that means all your y values y1, y2, yq are distinct, and that means there exists no collision which I obtained by running by a generalized algorithm. So, now it is easy to see that by applying simple rules of probability, we obtain that the probability that the event no collision q occurs is same as the product of these probabilities, namely the probability no collision occurs. Given that the event no collision 1 occurs, what is the probability that event no collision 2 occurs, and like that, given that the event no collision q minus 1 has occurred, that means the first q minus 1 queries gives you distinct output. What is the probability that even when you make the qth query, there exists still no collision. And if I multiply all these probabilities, I obtain the probability of the event no call sub q. Okay. So, let us calculate each of the probabilities that are there in your right hand side. So, it is easy to see trivially that the event no call 1 occurs with probability 1, because when you are making your first query, definitely no collision has occurred. That means y1 is distinct. So, I can simply turn off this, ignore this probability, because that is 1. Now, let us compute the ith term in the expression on your right hand side, namely let us compute the probability of the event no call sub I plus 1, given that the event no call sub I has occurred. That means your event is the following: your y1 to yi are all distinct, that is given to you, and then when you have made the query for xi, you have obtained xi plus 1, you have obtained yi plus 1, and we want to analyze what is the probability that this yi plus 1 is different from all the values y1 to yi, and it is not difficult to see that this probability is nothing but 1 minus I plus 1. Why? Because I minus I over n denotes the probability with which this I plus 1th value could be same as at least one of these I values, and if we subtract that quantity from 1, that gives you the required probability. And I can always replace this 1 minus I over n by e to the power minus I over n, and this comes from your basic inequality, which from the fact that 1 minus x can be always upper bounded by e to the power minus x for all x. So, now I know the value of each of the terms in my right hand side, that is what I have derived. So, what I have to do is I have to just substitute here. So, I obtain that the probability that the event no call sub q occurs is the product of these entities. Okay. And if I take the product in the exponent, basically I end up doing the summation in the exponent. So, I obtain that the event no call I occurs with this much probability, and if I take the summation inside, I obtain that this is less than equal to e to the power minus q times q minus 1 over 2 power 2n, and then I can finally replace it by this inequality, and this is because q over q minus 1 q times q minus 1 over 2n is less than n, because I am under the assumption, I am making the assumption that q is upper bounded by square root of 2n. If that is the case, then indeed q times q minus 1 over 2n is less than n, and if that is the case, then I can use the fact that e to the power minus x is less than equal to 1 minus x over 2. So, by making all this facts, using all these facts and doing the substitutions and solving the inequalities, I obtain that the event no call occurs with this much probability, but that is not our goal. Our goal was to compute the probability of the event call q comma n to occur, and since the event call no collision q and the event complementary event collision q comma n are related by this, we simply obtain that the probability of the event collision q comma n to occur is at least q times q minus 1 over 4n. So, that is the lower bound we have established here, assuming that your function h is a random function and we have evaluated the function h at q distinct x values, and we have established that the probability of the collision is at least this much. Now, you might be wondering that why this generic algorithm for finding the collision is called or is given a fancy name birthday attack. Basically, this is due to the fact that whatever analysis we have done, you can model is as a following computer science problem. Imagine that you have a set of q people sitting in a room who are their random set of people, and each of them has a birthday. So, you can imagine that a function h there is nothing here is nothing but it is a function which maps the people to their birthdays, and we assume that the birthdays of the people are falls in a non-leap year. So, the number of candidate birthdays which those people could have is 365 possible value, right. So, you have q number of people, say person 1, person 2 and person q, and their birthdays are h of p1, h of p2, h of p3 and so on, and we want to find out what is the probability that among those q people there exist at least 2 people who have the same birthday. I am not interested in the year when I am not arguing that I do not require that they should have same year of birth as well. I am just interested whether they have the same birthday or not, and you can imagine that the function h here is mapping those people to their birthdays. So, it turns out that whatever analysis we have done here in the context of hash function, it could be carried out even in the context of this birthday problem, and it could be proved that if there are 27 random people in their room, then the chance that at least 2 of them have the same birthday is approximately 50%. So, which is a good enough probability. You do not require large number of people to ensure that with good probability 2 people have the same birthday. Okay, so, coming back to the context of cryptographic hash functions. So, what exactly are the implications of this birthday attack? It says that imagine that your codomain space, its size is 2 to the power l. That means, your hash outputs could be any string of little l bits. Then what this birthday attacks the analysis of the birthday attack basically says is that if you evaluate your hash function at these many number of distinct inputs, namely 2 to the power l plus 1 over 2 number of distinct inputs, and if I substitute this value of q here in this expression and the value of n to be 2 to the power l, then I find that the probability of the collision turns out to be a constant independent of the size of l, and a constant success probability is a good enough probability for an adversary to find collision in your underlying hash function in a polynomial time. That means your value of little l has to be significantly large, and because if you ensure that your value of l is significantly large, that means to make these many number of queries, the adversary has to do an impractical amount of computation, and that will rule out the implications of birthday attack. Theoretically, the implications are still there. It is only that we are going to operate our underlying hash function with such a large value of little l that carrying out these many number of hash evaluations is going to be impractical, and that is why a necessary condition for obtaining a collision resistant hash function is that you should have a large value of little l, because if your little l is small, then just by making these many number of queries, adversary could come up with a collision with almost a constant success probability. So, that is why the minimum value of little l which is recommended for current practical instantiations of the hash functions is 256, because if you set L to be 256, then basically adversary has to do computations of order 2 to the power 128 to obtain collisions with a constant success probability, but 2 to the power 128 computations is really a huge amount of computation. So, now let us discuss another type of birthday attack which we call as a small space birthday attacks for finding the collision. The idea here remains the same. So, remember in the generalized collision finding algorithm, we evaluated the hash function at q number of distinct inputs, and we had to store all those hash values, because when we are comparing whether we have when we are comparing the x input and their hash values to find out whether there exists a collision or not, we need all the xi, xj pairs and their corresponding hash values. So, it turns out that the space complexity here is of order q. So, if you consider in the modern computer systems, time is not an issue or the processing speed is not an issue. Day by day the processing speed is increasing. What matters is the space complexity, because space is really a very critical resource here, and that is why what will be interesting here is whether we can carry out the birthday attack or the generalized birthday attack that we had seen earlier by not by where the space complexity is not O of q, but rather say it is a constant, right. Now, you might be wondering that how can just by storing constant number of values we can still perform an attack which is similar to the generalized attack that we had seen in the context of birthday attack. So, the idea behind this constant space complexity or a small space complexity birthday attack is as follows. So, imagine you have a sequence of values y1 to yq which are basically obtained by a sequence of a chain of hash evaluations. So, you will start with a say distinct or random y1, and then y2 is nothing but hash of y1, and then from this y2 I obtain y3 which is same as say hash of y2, which in turn is same as hash of y1 and so on. So, you can imagine that I have a chain like this, and each subsequent y value is related to the previous y value by the hash function h. So, that is how I have computed these y values. Now, we can prove that if you have two indices big I and big J, right, such that your yi value and the yj values are same, that means you have this chain of values y1, y2, and say you have two indices, intermediate indices yi and yj, and you have said done q number of such y evaluation y computations, and you have say two such indices y sub big I and y sub big j such that y sub big I and y sub big j are same, then it means that there exists at least one indice y sub little I or one y value which I denote by y sub little I, such that y sub little I and y sub 2 times little I will be same. That constitutes a collision for you, right. So, that is a claim here. Okay. So, I am not going into the details of the proofs of this claim, but you have to believe me that if indeed we have computed the y values like this, and if we have this condition to be there to be true, then this condition holds as well, right. And that gives you an idea of how to find a collision with a space complexity of constant, right. So, what you have to do is you have to perform the same analysis that you have done for the previous case, but now you just need to store two hash values. So, what you have to do is you have to in each iteration you have to compute the next y value. So, you have to go from yi to yi plus 1, and at the same time you have to keep a track of y of 2I as well, right. And as soon as you obtain an index little I such that y of y sub I and y sub 2I are same, that means there exists some collision in the sequence of y values that you have computed till 2I, y of 2I. So, what you have to do is basically then you have to do a backtracking and find out the exact collision. So, I stress there this claim does not give you the guarantee that y sub I and y sub 2I is exactly the collision, because y sub I is obtained from the value h of yi minus 1, and y sub 2I might be obtained by is obtained by evaluating y 2I minus 1, right. So, it is not guaranteed that yi minus 1 and y sub 2I minus 1 constitutes a collision. That is what you have to basically check by doing the backtracking, right. So, the interesting part here is that both for stage 1 as well as for stage 2 we just need to store two hash values. So, in stage 1 we can go in the forward direction and stop as soon as this condition holds, and which will become true with very high probability. We can prove that, and if indeed this condition becomes true we stop there, and then we do a backtracking again by just keeping track of two hash values, and we will end up finding the exact collision in the chain of values that we have computed, and the probability analysis more or less remains the same. So, that is the idea behind the small space birthday attacks for finding collisions. So, now let us discuss some additional applications of collision resistant hash functions. So, the major application that we had discussed in the last lecture was constructing message authentication codes for arbitrary length inputs. But in this lecture we will see some other applications as well. So, imagine you are given a collision resistant hash function, and one of the main ideas that we can use in several applications involving the hash function is that the hash of a file can serve as its short unique identifier, where the size of the identifier will be fixed, say little l bits, and its size will be little l bits irrespective of what file you are feeding as an input to the hash value. It could be a small file, it could be a large file, I do not care. The digest of the file will be taken as an identifier. And since we are assuming that your underlying hash function is collision resistant, that means in practical amount of time it will be very difficult to come up with two files, say x and x dash, such that both of them give you the same digest, right. Because if that is the case, that then this whole idea will not work. But since I am assuming that my underlying hash function is a collision resistant hash function, then it means that in practical amount of time it is very difficult to come up with two files x and x dash having the same identifier or the same message dash. And it turns out that this small concept you can use in several real world applications. So, let us discuss few of them. The first application that we can use, where we can use this idea, is that of virus fingerprinting. So, what we do here is that the antiviruses or virus scanner stores the hashes of known viruses in their database, and whenever we have an email attachment or we download an email application, and if we want to check whether the downloaded attachment or the download application has a virus or not, what we do is the virus scanner basically computes the hash of the downloaded attachment or the application, and then it matches the hash with the known hashes of the viruses which it has already stored in its database. And if there is a match, then an error message is given to us that it suspects that a attachment that we have obtained or the application that we have downloaded contains potential virus. Notice that this idea is not it might be possible that you have an attachment which is a genuine attachment, but unfortunately its hash matches the hash of one of the known viruses. In that case, even for a genuine attachment you might get an error message, but that implies that you are getting a collision or you are finding a collision in a feasible amount of time. But since I am assuming that my underlying hash function is collision resistant, if at all an error message is given to me, that means with very high probability indeed the hash of the attachment that I am downloading is containing viruses. The second application where we can use this idea is that of deduplication, and here the idea is that we want to eliminate duplicate copies of the same data. So, imagine that we are in a cloud storage scenario where say we have several users, users 1, user 2 and say n number of users, and each of them are hiring a common cloud storage for uploading their data. Now, since the users are independent of each other, it might be possible that say user 1 and user 2 end up uploading a same file, and if the cloud storage naively gives or stores both the copies of X, then that will be a wastage of space. So, what can be an interesting or smart solution will be every time a user tries to upload a file, what the cloud storage can do is can compute a hash of the file for which the request has come, and it can compare that hash value with all the hashes of the previous file that it has stored. If the hash value matches, that means that the file which is now coming to which has been requested to be uploaded is already there in the cloud storage. So, no need to again create a fresh copy of that file. So, that is the idea of deduplication here, and again we are using the idea of hashing the file and using the hash of the file as its identifier. Now, let us see some other applications of hash functions, and this is what we call as hash pointers. So, I am assuming that all of you are familiar with pointers in programming language. Basically, pointers are special type of it's a special type of variable, or you can imagine that basically pointer variable points to a memory location where some data is stored. So, if say 1884 is a memory location, and if I have a pointer variable, then in that pointer variable the address 1884 is stored. So, by following the address by following this pointer you can come to the location 1884 and see what exactly is stored here. Now, this hash pointer is almost same as a pointer in spirit, but apart from pointing to the data, this pointer also stores the hash of the value that is stored in that location. That means, if this is some data which is stored in some arbitrary location, and if I say that this is your hash pointer, then this hash pointer will have a pointer to the data as well as the hash of the data that is stored in that location. And the advantage of this hash pointer is that by following this pointer, not only you can retrieve the data, right. So, if you follow the pointer, you can retrieve the data, and once the data is retrieved, if you want to verify whether you have retrieved the right data or not, you can again hash it and compare it with the hash value which is stored along with this pointer. So, that is the advantage or the extra property which is available with the hash pointer compared to the traditional pointers. Now, it turns out that any data structure which we can design using the standard pointers in programming language, all of them can be redesigned by replacing the standard pointers using hash pointers. So, for instance, this is your standard linked list where you have a collection of nodes, and each node has some sequence of data, of which we call as data block, and the pointer to the next block, right. And like this, so this is your last block, and since there is nothing after it, that is why the next or the next pointer for it is set to be null, and we have the previous block where we have the data and a pointer pointing to the next block, and so on, and like that we have the head pointer. So, that is a standard linked list here, which I guess all of you might be aware of. And what we now do is that we take the same linked list, but replace all the pointers by hash pointers. So, we have now a sequence of blocks here. Each block will have its own data contents, and along with that, instead of a regular pointer, we have a hash pointer which will point to the block after it along with the hash of the data as well as the hash pointer stored there. So, that means, if I consider this hash pointer, right. So, here it will point to the next node, and when I say node, node means node as a whole, that means the data concatenated with the hash pointer stored there. So, this hash pointer will be pointing to this data block, and along with that a hash of this whole block, whole binary string, whole binary content that is kept here will be stored in this hash pointer, right. And now, it turns out that as soon as I take this standard linked list and replace all the pointers by a hash pointers, I obtain a very nice data structure which has a very fancy name in this today's world, namely blockchain. So, if someone asks you what exactly is a blockchain, blockchain is nothing but a linear linked list where all the pointers are replaced by hash pointers. That means, you have a sequence of blocks, each block has its own data part and the short hash or the short summary of the entire content of the block after it, and so on, and like that you have a short summary of the entire blockchain or the entire linked list, which is nothing but the hash value of the head data block, right. So, this blockchain, it gives you a very nice data structure, namely it helps you to instantiate what we call as tamper-evident log. And what exactly is a tamper-evident log? It is a log data structure, namely it will store lot of information, and it should be a dynamic data structure in the sense it should allow you to append data to the log. That means, whatever existing log you have, you can append data to it, and apart from that, any change in that log or the existing log should be deductible. So, let us see whether we can instantiate this tamper-evident log using blockchain. So, it turns out that indeed we can use the blockchain as a to instantiate tamper-evident log, and the idea here is that we can use the head hash pointer as a short summary for the entire log. That means, I do not need to store the entire log, it is enough for me if I just store the head hash pointer. But just storing the head hash pointer, I can detect later on whether any tampering has occurred in the existing log or not, right. So, let us see how exactly the things go here. So, if at all you want to insert a new data, that means, suppose if this is an existing blockchain and if you want to insert a new data block here or a new node here, that is very simple, right. So, you create the data, whatever data you want to store, and along with that you create a hash pointer here which will point now to the previous head block here, and once you do that, you create a hash of this entire thing, and that will be the hash pointer which will be now stored in the summary of this tamper-evident log. So, the inserting a new data here is exactly the same as the insertion operation in the standard linked list. But now the interesting part here is that any change which adversary tries to make in an existing log, with very high probability it will be deducted. So, I imagine for instance say the adversary tries to change the contents of the data block in the third node here, right. So, at the moment I am assuming that you do not have the existing data, you do not have the existing blockchain, you just have the head hash pointer with you. And now you ask someone that you please give me the content of the third node here, or you give me the entire blockchain. So, suppose if the request goes to the adversary, then what the adversary can try to do is that instead of giving you a genuine copy of the whole log or the whole blockchain, he might now try to insert his own data, or he might want to change the existing data and so on, and now he might want to give you the changed blockchain. So, the idea here is that if at all he tries to do that, he will be detected with very high probability, assuming that your underlying hash function is a collision resistant hash function. Let us see how it happens. So, imagine it changed the contents of the data block in the third node, and as soon as it changes here, this node is now going to be a new node. That means the binary content will differ, and to make it consistent he has to change the hash pointer here, namely he has to change the hash value here. As soon as he changes the hash value in the second node, the node 2 as a whole, its binary content becomes different. So, to make it consistent, what he has to do, the adversary has to now change the hash pointer which is stored in the first node, and as soon as the adversary changes the hash pointer in the first node, the binary contents of the first node will become different. And to make it consistent, basically adversary now has to change the contents of the head hash pointer as well. But as soon as he changes the head hash pointer, that will not match with the head hash pointer which you have stored with you, assuming that finding collisions is difficult. Because if finding collisions is difficult, then it may so happen that this changed first node, its hash value matches the head hash value that you have stored with you for the existing blockchain. But assuming finding collisions are difficult, the adversary will be deducted with very high probability. And that is why the blockchain is a very popular database, because you can keep on adding data to the existing log, and the whole log can be summarized by just storing a small hash value. Now, let us see the last application of hash function for today's lecture, and this is a very nice application which we call as Merkle tree. And what basically Merkle trees are, they are full binary trees with hash pointers, right. So, all of you, I am sure you know what exactly is a full binary tree. You have so you have say 2 to the power k number of leaves, and each layer you have both the nodes, at each layer you have a node with both its left child as well as right child being present here. So, what we are now doing is that instead of implementing the binary tree with standard pointers, we now replace those standard pointers using hash pointers. So, we imagine that we have say 2 to the power k number of data contents or data blocks here. So, in this example I am taking say 8 number of blocks, and the way we construct a Merkle tree is as follows. So, we have at the leaves the data blocks present, and then we go to the one layer up where we have the hash pointer. So, this hash pointer basically contains the hash of the data, and this hash pointers basically contains the hash of this data, and so on. And now what we do is, since these hash values are also binary strings, we can take this binary string, concatenate it with this binary string and hash it and go one layer up. So, this hash value basically is a hash value of concatenation of these two hash values. In the same way, this hash value is basically a hash value of the concatenation of these two hash values, and so on. And we go one layer up, and like this we keep on going till we obtain the hash root pointer, and that hash root pointer or the hash value which is stored at the root basically is a short summary of the entire tree, right. And we require that in this Merkle tree the number of leaf nodes should be a power of 2. If that is not the case, then we append dummy nodes to ensure that the number of leaf nodes is indeed some power of 2, and that is required for the overall application here. So, as it was the case for blockchain or the hash pointer based linked list, it turns out that any change or any tampering of data block can be easily detected if someone is maintaining up to date copy of the hash root pointer. That means, imagine I as a user, I am not maintaining the whole tree, I am just having a hash root pointer with me, and suppose at a later point of time I ask someone that please give me all the data block contents, then if that user tries to changes the data block or the data content, then with very high probability it will be deducted, assuming finding collisions in the underlying hash function is difficult. So, for instance, suppose it tries to change the second data block while giving it back to me. If it changes the second data block, then the hash value stored in the previous tree will get changed here, and as a result this binary string or this node as a whole will become different. To make it consistent, the adversary has to change this hash value, which will further disturb this whole binary string as a whole. To make it further consistent, the adversary has to change this hash value, and this as a whole will make this binary string disturbed, and as a result the adversary has to change the head hash pointer or the root hash pointer, assuming that finding collisions are difficult, but as soon as the adversary tries to change the root hash pointer, it will be deducted because that won't match with the root pointer that I am storing with me. The interesting part of this Merkle trees is the proof of membership. So, what exactly is the scenario here? Imagine that I have stored with me only the head root pointer with me, and I do not have the data blocks with me. Now, suppose later on I ask someone that please give me ith data block. Now, the person from whom I am asking the ith data block, if he is a malicious person, he might try to give me an incorrect ith data block. How do I verify that whether indeed the so called ith data block that he is giving to me is a correct data block or not? Well, one way of verifying that is that I recompute the entire tree, but for recomputing the entire tree, not only I need the ith data block, but I need all the data blocks which were present in the original Merkle tree. Because only when I have all the data blocks present with me, I can recompute the root along by and taking the ith data block that the person is giving to me, and then verify whether indeed he is giving me the correct data block or not. But it turns out that we do not require all the data blocks, namely 2 to the power k data blocks, as a proof to verify whether the retrieved ith block is indeed the current ith block or not. Magically, it turns out that only by giving you k number of data blocks, one data block and k number of intermediate blocks, it suffices for me to recompute the root here. So, basically that acts as a proof for the person who is giving me back the ith block, right. So, if he is giving me back the ith block and he wants to prove that indeed the block that he is giving to me is the current ith block or not, basically what he has to do is that apart from that ith data block, he can give me all the blocks along the path from the root to the data block. And just by using the blocks along the path from the root to the data block, which I have actually asked for, I can recompute back the root pointer or the root hash value and compare it with the root hash value that I have stored with me to verify whether indeed the data block that I have received is correct or not. So, let me demonstrate what I am trying to say. Imagine I have the up to date root pointer or root hash value, and I asked from a person who is actually maintaining a full copy of the Merkle tree that please give me the sixth block here, 1, 2, 3, sixth block here, and he gives me the sixth block. And if I consider the path from the root to the sixth block, the nodes that are occurring along that path are now highlighted with this highlighted blocks. And what basically that person has to do is he can give me the sixth block, and along with that he can give me all the binary strings along with this highlighted nodes. And these highlighted values suffice for me to recompute back the root of the original tree, and by recomputing the root of the original tree I can compare it with the root value that I have stored with me, and assuming finding collisions in the hash functions are difficult, with very high probability it is ensured that indeed the so called sixth block that the person has given to me is indeed the correct sixth block which was present in the original Merkle tree. So, that means now you can see that the number of values that the adversary that the person has to give me to prove that indeed he is supplying me the correct ith block is not of order 2 to the power k. Basically, for each layer of this complete binary tree, he has to just give me one node value, right. So, at this layer he has to give me the binary contents here. At the second layer he has to give me the binary contents of this node. At the third layer he has to give me the binary contents of this node, and at the last layer basically he has to give me the ith data block, in this case the 6th data block. That means if you have a Merkle tree where there are 2 to the power k number of data blocks, and if you want to fetch only a particular data block, ith data block, then the number of binary strings which the adversary which the receiver has to, which the person has to give back to me is of order k only, not 2 to the power k. And that makes this data structure very powerful. You can prove the membership of certain data blocks in the whole tree without actually supplying the whole tree. Just supplying logarithmic number of information, it suffices for an entity to prove whether a certain data block is present in the tree or not. Right. So, that brings me to the end of this lecture. Just to summarize, in this lecture we had seen some of the applications of hash functions. Right. We had seen how the hash of a file can, or a hash of an entity can serve as its unique identifier, assuming finding collisions are difficult, and this concept has got tremendous applications. A major application is in the context of hash pointers, where we can replace all the data structures based on standard pointers by hash pointers, and we had seen how blockchains can be used as a tamper-evident log based on this principle. We had also seen Merkle trees and how Merkle trees helps us for the efficient proof of membership. Thank you.